Alrighty, back at it with some more energy calculations. This time, a long cable carries current in one direction uniformly distributed over its circular cross-section. The current returns along the surface. There is a very thin insulating sheath separating the current, so what they're trying to say is that this isn't going to inflect on one another or infer outside of any self-inductance that we might have to incorporate. So that's what we want to find, is find the self-inductance per unit length. All right. So we know that the energy stored via inductance is 1/2 Li squared, and the energy stored via the magnetic field, seems like we've seen this playbook before, 1/2𝜇0 B squared d tau. Alrighty, let's get after it. It turns out we have indeed seen this playbook before, and we see that the inductance via the energy stored, where the energy is calculated from the magnetic field, can be lined up as such. L is equal to 2W/I squared, and if we plug in the W, we see that the 2's cancel from the magnetic field formulation. And then we see that L is equal to 1/𝜇0I squared times the integral over all space of B squared d tau. Well, we know that we can find the magnetic field via Ampere's law. So the line integral of B is equal to 𝜇0I enclosed. So again, if our Amperian loop is a circle of 2πs, then we know that the current enclosed is the S current divided by the ratio of the S length out to the R length out. Okay, because again, we had current traveling down it and then returning on the outside of the shell. So if the Amperian loop takes into account both of those layers, then we're going to have to take into account both the I enclosed. So outside of that, that's probably the only sticking point for this particular question. Solve that for B, and we see that we get 𝜇0 IS over 2πr squared. And now we're ready to square that and chug away. And if we want the self-inductance per unit length, then we need to take the inductance and divide it by L. And again, it doesn't really affect our integral much. We're still going to we'll just put that in the denominator that we had in the first point. But yeah, we see that the integral goes from 0 to L, 0 to 2π, 0 to R, for some length L, radius R, and again 2π, we like that. Nothing here is really to worry about. We have a factor of S squared that comes from the magnetic field squared. Everything else we can start to simplify and cancel. We see that we shove all the constants outside in part 2. In line 3, we cancel 𝜇0I squared from the denominator and the numerator. And then we split up the integrals. Thank you again, 𝘭𝘵𝘵. And then we simplify down even more. So we see that we get a factor of L that cancels, a factor of 2π that cancels, and a factor of R to the 4th that cancels. This simplifies, oddly enough, to 𝜇0 over 8π. So this tells us that this is independent of R, which is actually kind of cool. Didn't think this would be the case, but the math checks out. So we could use this for any kind of, radius that we want. Pretty cool, though.